Okay, I think we'll get started. So these slides, by the way, are available on TinyURL. So this is the exact same ones that I'm showing you. And that's my Twitter, which I have public DMs on. You're welcome to, I didn't put my email address, but you're welcome to just kind of private DM me and I can give you contact info. I forgot to mention that in one of my morning ones. This is my third session, so I'm a little bit tired today. But we'll get through this. This is an interesting talk. So a little bit about me. I'm not a active practice. I don't do genetic algorithms for work. I'm just a super enthusiast. So I will. This will be a gentle introduction. I'm currently lead engineer at Yard Club, which is kind of like it's a San Francisco company. I just moved here after 15 years in SF. Yard Club's kind of an Airbnb for heavy construction equipment. We just we're in the middle of an acquisition. I have a couple of side projects, so if I see some familiar faces from one of my morning sessions here. Before that, I was at Adobe through some more acquisitions 5 years ago. And then before that, I was in the engineer in the toy industry and also pro audio gear. So hopefully we'll be doing genetic algorithms at some point in the future if they ever come back in style. I'll start with some applications just to kind of like hopefully whet the appetite. Does anybody know genetic what they are really? I'll get into the. Anybody use them for work, by the way, for optimizations or anything? Okay, cool. In Minneapolis, like a Minnesota company? Cool, yep. Okay. What's the name of that company, by the way?
Lasix Industries.
Okay, cool. So I'll take you through a few applications, and we'll actually get into at a high level how this works. So let me give you just a brief intro. So basically, it's using the principles of evolution to design an algorithm that automatically either writes software or, in this case, evolves hardware. So what I just did, I put these images in last night, so they're not probably the best, so I'll try to do my best to explain. So what you're looking at here is a drawing of basically a reconfigurable FPGA. An FPGA is basically a chip that you can program. This is not new. This is very old, but genetic algorithms have been used to evolve the logic gates. Basically, the connections within the FPGA are what kind of determine the logic that is represented on the device, and that lets you do whatever you need to do. Usually, this takes a team of engineers to program it in Verilog or VHDL, do a lot of verification on the device with on a larger breadboard, or well, not a breadboard, but a circuit board, until you get to what you're looking for. Genetic algorithms can be used to basically start with random connections and eventually get to your desired function. Automated design. So this is an antenna that doesn't really look like a normal antenna, but the shape was actually evolved. And this antenna was actually went into orbit on a space shuttle. It was designed by a friend of mine, Greg Hornby, who's got a paper. I don't know if I have the link for it here, but it's probably something I can get to you guys. But he basically wrote an algorithm to evolve an antenna, giving it certain constraints. It needed certain power, needed to operate at a certain low power consumption, and needed to be at certain frequencies. And the algorithm evolved this weird shape, which would not look like anything that a human is usually taught to design. But it fit all the constraints, and it came in a lot smaller than a regular antenna would, and it performed just as good as any antenna, any man-made antenna. Evolvable robots. So there's a bit of a quote here, but this robot was evolved at the, I don't know how to pronounce it, but the Fraunhofer Institute, the institute in Germany that invented the MP3. They do a lot of research. And they are looking at evolving robots to do, dangerous work or physical labor, or this was actually an evolved 3D printed design. So no, I'm not actually sure what it's supposed to do, but I'm sure it fit its parameters. Here's something that's a little bit more easy to understand. This is not, in here, the hardware was not designed, but the neural network that controls it was evolved. And so basically it's a raw robot. A neural network is usually trained through traditional, like backpropagation, if I won't get into really what that is, but a lot of directed math to evolve its motion. Or you could say, here's the robot, here's what it needs to do. Here are the sensors, infrared sensors, sound sensors in this case, a camera, touch sensors on the grippers. Connects basically through a bunch of layers of neurons, connect eventually to motors, which move, and apparently a speaker. Basically evolve the coefficients that weight the connections between these neurons into something that doesn't fall off the table or doesn't basically just get stalled. So this is another common application of genetic algorithms, is to evolve the coefficients between neurons in a neural network to behave properly. So a little bit on how to evolve. All genetic algorithms go through the same high-level process. You start with a population. So this, you'll see a lot, obviously there's parallels with the natural world, and because that's where this was inspired from. But what I mean by population is basically each row is an array of integers, and each of these each group of integers could basically represent something about the design of what you're trying to evolve. So, for example, in this case, let's take one row at a time. Each of those numbers could be a weight between a neuron. And at the beginning, the algorithm basically sets all these numbers at random. And so you start with an initial population that's totally random. The robot or whatever you're trying to evolve is going to look like it's going to behave terribly. It's probably going to stall if it even moves at all. If it's an antenna, it's just going to be a random shape. But you're going to have basically, if each of these represent one instantiation of what you're trying to evolve, you'll just get, in the case of the antenna, you'll just get 100 random shapes, and they'll probably all perform like shit. What happens then is you take your initial population and you have what's called a fitness function. And the fitness function is what your ideal goal is, the perfect antenna. So it should fit all your parameters. It should operate at a low enough power. It should operate at the right frequency. In the case of the robot, the fitness function could just be, hey, did this robot die? Or did this robot crash into something? It could be a binary answer, or it could be more of a grade. But what happens? But an important part is you have your population, and then you evaluate each of them, and you rank them. And then the principle of natural selection comes in, where you select the parents. Obviously, you want the best performing. Those were the array. Think of those arrays as chromosomes. They're typically referred to as chromosomes to further the analogy. And basically, you pick your top performing chromosomes and you select them to move on to the next generation. Now, you don't just simply copy them to the next generation. You basically have what's I will keep it the clean version, but basically, you take two parents. You combine them together, and you get offspring. This is literally what happens. So you do this. You take parents, and you probably, out of your pool of your pool of your top performers, you randomly select parents and you just create offspring to kind of create a new generation. And maybe you keep some of your original parents around because you want to keep some, or maybe you keep even some of your worst performers around, because what tends to happen is even if in one population there are bad performers, they might have a characteristic which you want to actually keep around. There might be, for example, there are many reasons why a chromosome might fail, but it could have some aspect of it which would be important to keep around maybe for a later generation. Maybe there's some, I don't know, maybe it evolved in a ear that while it has no other limbs, it's obviously going to have a very low score, but you want to kind of keep that ear around because, hey, it did evolve something that's going to be useful for later. I hope that makes some sense. This is going to get kind of weird pretty quick if it doesn't. So a second common operation that's performed is just straight up mutation, and that can be achieved literally just by flipping a bit or changing a number in some subset of your population. And what this does is it adds like a digital diversity, basically, because you start with initial population, and if you just mix and match, you're not going to achieve diversity. And this is something that also comes from the principle of natural selection, where there's probably environmental factors that can kind of like create a random flip, or there are genes that flip. I'm not a biologist, but in the natural world, there is an analogy to this. Then you basically repeat until you get the desired fitness. So this could take a long time. That antenna that I showed you that went into space took 4 weeks just to evolve from randomness to a proper antenna. And this was 10 years ago, and I think things have changed, and hopefully that could be done a lot quicker now, but it takes a long time sometimes, and depending on what you're trying to evaluate, for you to achieve, for you to get to something that's workable. But the thing is, no human intervention, pretty much no human intervention is required once you've kicked off the process. And that's really, for a lazy person like me, and if you've been to my side project session, this is one of the great, obviously, attractions to this way of solving a problem. The other thing is, like in the case of the antenna, you will often evolve something that is not taught in schools, or is not kind of thought as a best practice. There's a paper on an FPGA that was evolved to, I forget what it was. Yeah, that one. Yeah, right. You know what I'm talking about? The Adrian Thompson paper. Yeah. So there was an FPGA that had a microphone, and it had a simple task. It was to differentiate between two different frequencies, and then turned out that basically the best performer after the entire process had completed, the researchers did not understand how this circuit worked. And it turned out that there was some weird deviation, there's like a capacitance difference on the circuit board, which was outside of the chip, that was being used as an advantage for the circuit as it was evolving. And so once they basically, what happened was once they moved a wire near the board, the circuit stopped working. And so, a little bit creepy, but it basically, this evolution process used an environmental factor that would not have been even considered by a human being. And so here is actually another, should have put this earlier maybe, but here is a kind of a look at how an algorithm like this is designed. Basically, you start with a constraint, and each of the lengths and the angles are represented, in the genotype, in the chromosome, that array of integers. It could be, I think it says it at the bottom, right? One of the constraints was it should have 4 wires, and so the lengths of each of the wires were represented as integers in each in each chromosome, and eventually, so it started as random, and eventually it would get to the ultimate solution. That sounds even creepier, but coevolution. So I just want to mention. So this is another layer on top of genetic algorithms where you're not just. So in some cases, you're not just evolving. You're not just evolving a population in a vacuum. You can evolve 2 different types. You can evolve, especially in the case of a robot, you can evolve a host and a parasite, and a predator and a prey. So you can evolve behavior you can evolve 2 different behaviors in the same environment, and if they can compete against each other, they can actually affect and help the other organisms or the other digital organisms performance and basically get to completion faster. So this is another key aspect or it's another optimization. Future trends, getting to my last slides, but I've noticed, so genetic algorithms, they were hot when I got into them like 10, 12 years ago, but they fell out of favor fast. And I think a lot of the reason had to do with it just takes so freaking long to run these programs. But this was before AWS was around, this was before GPUs were around, this was before GPUs were on AWS. I feel, and I hope that this type of problem solving is ripe for a comeback, because neural networks were also out of favor for a long time. And deep learning is basically neural networks with more hidden neurons. And in my opinion, there might be better experts here, but I think one of the reasons they came back was because processing power got a lot easier to scale. And one reason why I want to talk about this at this conference was for me to read up again on what's going on in the field, and it looks like not a lot has happened since I left like 10 years ago. But I'm hoping there could be a resurgence and at least curiosity. So if anybody else knows I'd like to hear more about the fellow, and I'm going to totally put him on the spot about what you guys are working on. And
you want to hear about it? Yeah. It's another good application. So we were making laser cutting equipment, and so when you want to cut target price tags out with a laser, you can put 4 lines on the screen, and then it's going to, obviously going along a path in a square is going to be the fastest way to cut that price tag, right? Well, what if it's a picture of a Christmas tree, and you have like 800 vectors on the screen? Well, when you design it in Adobe Illustrator, the designer just draws the Christmas tree. It could be any order. And then when you load it into the CAD software for the laser to actually cut it out, you end up with a really long path. And so you're interested in solving the shortest path problem, which is a very common computer science example. It's like the traveling salesman problem. And so if you Google traveling salesman genetic algorithm, there's this really awesome couple of videos on YouTube. And we did it one day, and we're like, holy cow, we could just use this library to take Illustrator files and then shorten the vector path for an arbitrary thing. And so we actually have a couple of snake sorts, a really easy way to do it. You just take vertices that are closest in a snake pattern going up the screen. The problem is then you get long lines, you end up with long jumps. And so we did some research on actually implementing a genetic algorithm in our software to do the sorts faster. And it wasn't faster. Same problem that you had. It took way too long to calculate and converge on an answer. But it's a really good example of how this technology can be used.
Another classic.
I think that's what you hear a lot is it worked, it took too long.
Yeah.
And so we are not going to do any more research on it. But I feel like I swear, it's got to come back.
Could you touch on what done means? When you say it takes too long, you get an answer in hours, right? As you iterate and keep doing stuff.
Well, you get, so the thing is you get, so I'm going to totally butcher math, but there's a solution space, obviously, that's almost infinite, right? But what happens is you can get stuck in local maximas local minimas or local, whatever, but you're not going to necessarily find the optimal solution. And you could be skating, you could be basically going around and not improving for a long time. And then it could take, I mean, it's one reason why you have mutations, but they don't always solve the problem, is you need to get a jump, kind of like what happened supposedly in, obviously, well, it's a fact, right? Natural evolution. Like, it took a long time and there were step functions, but that's what you tend to get stuck a lot. That's one problem. And the other problem is you can have, the fitness functions can take a long time. And yeah, converging can take a long time, and the fitness functions could take a long time, is from what my understanding. Well, I guess you don't. Yeah. It's optimal that I don't have to work on it. That's the I don't have to think about it. Well, yeah. So your fitness function should. I mean, your fitness function shouldn't be like something you're not happy with. It should be like, this is my goal. You have a goal, but in terms of what the absolute final numbers are,
A lot of people will stop it when the rate of change goes down.
Yes,
to a certain
right,
percentage.
right.
Initially, you get a lot of change. It changes very, very dramatically early on, and then maybe after running for 10 minutes, it only changes by 5% or 1% on an iteration.
So there could be some strategies where when that happens, you kick in some other trigger that maybe swaps in a brand new population for half of your population. There's a bunch of strategies that you can do to get around that. But that's why it just makes it take even longer. So.
Sometimes you do that artificially, like with simulated annealing. You let it change drastically at the beginning of your simulation, and then over time you let it harden to try to escape any of those local minimums and local maximums.
Yep.
So I'm curious, in the case of the antenna, like in order to do the fitness function on each one of those offspring, wouldn't they have to actually build that antenna?
No, you simulate it. Yeah.
Electromagnetic simulator.
How?
They have electromagnetic simulator, so they know the E&M wave functions, and so like SolidWorks or ANSYS then can take that shape, simulate it, and give you your wave pattern, and then you can feed that back into the function. Yeah.
They can tell just by the shape.
Yeah, oh yeah, it'll simulate exactly how the wave comes off. Of it.
Yeah, if they had flown on the shuttle for every single chromosome, that would have been taken a long time, more than 4 weeks. Yep.
You're talking about keeping some of the worst performers.
Yep.
How would you programmatically define keeping it, or do you just pick a random subset of those performers?
Yep. 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 Up front.
At a lower level,
Yep.
what are you using to solve some of the problems? Like if we're looking at, say, a traveling salesman problem, are we doing discrete mathematics, or are we doing some
For your fitness function, you could be using any math, but in terms of the algorithm, you could use any language.
There's libraries.
Lisp is really popular, but just because of how you can write the function. But I don't know if you.
Yeah, so a lot
sorry.
of the math behind this is really dicey, and that's why maybe it fell out of favor. But what we found was there's actually some really good .NET libraries. If you know CSharp, you can just pull in a DLL, and they give you a lot of the really common functions that the genetic algorithm needs. And so then you can write your program a lot more effectively that way. Rather than figuring out all this heavy math, there's just these like zeta functions and things that you'll read about in the books, what they're supposed to do for you, and then you implement it in a DLL, and so you just pull it in with the library.
There's some good stuff in Python too on GitHub. If you take a look, I meant to make a list of those, but. What's that?
I thought Apache had a framework to do genetic algorithms for a bit.
Yeah.
I would imagine that project's dead right now.
Probably. Yeah, that sounds familiar. DM me on Twitter and I'll look it up. Yep. Actually back there with the hat.
So you talk about like your hope for the future that will come back.
Is that a Muni t-shirt, by the way?
It is.
Nice. Okay.
It's your hope for the future is that they'll come back into fashion. How we have faster computers, etc. Things of isn't there like a fundamental paradox? Like the goal of actual evolution is to come up with novel solutions, but the fitness function is it better than the other thing?
Yep.
Not is it optimal for the problem? And applying it to this situation seems like we'll have faster computers, so we'll throw harder problems, and it'll always be too slow for remediation, right?
No, because you might have different constraints for a similar problem. You just don't want to have to think about the solution for it.
If you think about the problem I gave you, where you want to solve everybody's Christmas tree, like on the production floor, then it's not going to work, because it takes like 4 hours to solve a Christmas tree. But the antenna's a really good example, because he only needs to solve the problem once, and then he puts it on the spaceship, and it runs for a really long time.
Right, and that's the novel solution that
Yeah.
will take, Whereas your use case might be something that a human would not want to do,
Yeah,
but could do.
but could do, yeah.
That's the beauty of like constraint programming and genetic algorithms. It's like you don't have to get to the answer, you just need to know what the answer looks like.
Right. And so, designing those fitness functions.
That's the key.
If you do a lot of work in making sure you're doing that, then you've kind of just solved the problem. Like, in a lot of cases.
You understand it a
You know,
lot better.
You
understand
understand
the
enough
problem.
that you might need to just solve it without.
I just looked it up. Apache Commons does have a genetic algorithm package that was just published August of last year.
Whoa. Okay, I should read that. It's probably yeah.
So once I have a fitness function, what characteristics of the problem would you try a genetic algorithm instead of say just gradient descent?
I don't know. Does anybody know the difference, like when you would use GAs versus gradient descent? I don't know enough about gradient descent to decide between one of the two.
Just using that as a short for classical algorithms, I guess.
Because yeah.
If it's too hard to do with classical algorithms. Yeah, that's where I get genetic algorithms. Like, I had no idea how to do it. So let randomness figure it out.
Yes, I like that.
Yeah.
But really, what was your interest in? I mean, you said you're interested in genetic algorithms. Have you pursued anything in particular, or are you applying them to?
No, I'm not applying to anything right now. I wanted to evolve neural networks because I was in the toy industry, so we were doing a lot of kids' toys, and obviously wanted to make the creepiest kid toys as possible. So I think it probably came from that, and then I met Greg. I went to Gecko 2004. So, but it's a whole conference on genetic algorithms. It still happens. So, and I just got sucked into all the different applications. There's prosthetic hands that are trained to, feel and kind of move naturally. Not feel, but like move naturally. Maybe feel too. So there were so many applications that I just got sucked into the whole thing. But like neural networks at the time were dead. I mean, in the early 2000s, nobody was really doing them like they're doing now, and GAs kind of went the same way. Yeah. Android shirt.
To your question, at least from one perspective, the gradient descent is more of an iterative process. We're just going to say, all right, here was our result. Let's move it slightly closer to the result we desired. With this, we're going to create those random mutations of population genes that are going to allow for large use of new connections. And say, hey, we didn't anticipate this. So the gradient descent is going to say, let's adjust it slightly. One single algorithm, make it slightly better. Let's take 4 good algorithms, combine them together, and then take the best out of that, combine it with the best of something else. So it's a different way of looking at it. Could be accomplishing the same problem, but
And actually, going back to Muni Guy, I don't necessarily like. My idea is like not necessarily even stopping the algorithm ever. Like you can get to a good solution and then just kind of keep it going. Maybe tweak your fitness function a little bit, or add another part of the chromosome, add some other input parameter too, because that's another important aspect of it. So I see algorithms just continuing forever. You just pick out the ones that actually work, and then maybe a better one comes around later.
Right, and covering the changes, like incorporating changes in environment to your fitness.
Right.
Like, and just letting it be a system that can just.
This is pure speculation for me, but yeah, it seems to make sense.
Does it do like unsupervised learning?
Yes. Yeah. The supervision is kind of like, there's no active supervision. It's guided, I would say. Yep.
right now I have a problem I want to go solve. I want to go play with this. Can you give me some direction?
Yeah, let's connect on email. Yeah, I meant to put a list of libraries like But yeah, we can go through a little more specific ones too. Mhm. That's the dumbest question. I'm just kidding. Yeah. So what you so the if you I mean if you have, let's say you had 100,000 chromosomes, you run them each on an EC2 box or a Lambda. None of this stuff existed when last time I looked at it, but that's what I would do. And then you got all your answers at once, and then move on. And not only that, but now you can do it on a GPU, which is infinitely, I'm so bad at math, but it's just, you know what I mean. That's my answer to everything, you know what I mean. Yeah, I mean, so I haven't used some of this technology, so I mean, I would love to, if anybody wants to, hack on some stuff at some point and just see if this works, or at least works faster. Yep.
You mentioned Lambda in your talk earlier this morning about side projects. Do you have any other use cases of some of this, to your first talk?
Of Lambdas, or of this to my first talk?
Yeah. Is there any side projects that
No, not that I'm working on right now. I've enough. I would love to, but I'm not going to pretend to think that I have any. I haven't put any thought into side projects with this because I feel like there's a lot I need to still learn about. I need to jump back into this and learn a lot about it, and then kind of think about what this could actually be used for best now. Yeah. But let's keep in touch, and I'll let you know if and when I do a side project with genetic algorithms.
You search CUDA framework, that's a
Yep.
GPU framework, and then throw genetic algorithms on that search, you'll find all sorts of people using it.
Yeah, I mean, last time when GAs were hot, I mean, CUDA was new, and CUDA you had to get a card, a $1,500 card, put it into your desktop. There was no.
Not anymore.
Right. There was no cloud GPU at all. On-demand GPU. So. Anybody else? No. Cool. Well, thank you. Maybe we can hit the bar early.